Hi everybody. What we're going to do in this video is talk about how to analyze a between subjects ANOVA with one independent variable. I'm going to walk through data screening in Excel, the analysis with post hocs and effect size in JASP, power in GPower, and graphs finally in Excel. So we're going to work our way completely through one of these analyses. Okay. So I'm going to start with my CSV file that's provided as the data set. I'm going to open that up in Excel. The nice thing about JASP is that we will be able to use some of the data analysis screening functions that it has as part of ANOVA. Okay. Now this is a very simple data set, and thankfully it'll be much easier to do data screening than let's say a more complex or the last video on data screening. But remember, we still need to check accuracy, missing data, outliers, and our assumptions. Okay, so we're going to work through all of those first. Okay. So starting with, I'm just going to save my file as a regular Excel file, just for data screening. Okay. That allows me to work with this file and do some of the things I need to do, and then also allow me to save multiple tabs. So remember, I'm going to say this first one is my master data set. And then there's not going to be just a whole lot we're going to do to this data because it's so simple. But if we follow kind of the pattern we did last time, this would be our no typos page, which might be the end of it. I mean, we clearly don't have any missing data, so there's no issues with that. We may or may not have outliers to deal with, so this may be the last data set we have to create in a sense, and we may end up using the master data set as our data set if there's nothing wrong with it. So when I only have 11 data points, it's very easy to just visually look at this, but the purpose of this is to show you how to do some of this stuff. So let's look at accuracy. So to do that, I'm going to click on Data, and our data analysis button. Remember, to start with accuracy, we just did Descriptive Statistics, clicked OK. We highlighted the range of all of the continuous data, and then I just said, yeah, sure, why not? Let's do it. Oh, right, you have to click Summary Statistics, where it gets grumpy. And I forgot to click Labels in the first row. There we go. So now I can look at just what are the statistics for this column overall, but mainly I'm concerned with the min and the max. Okay, so for a friends category, so this is the number of friends I have by health condition. So this is an example from one of my undergrad stats classes. And I just want to make sure that's not negative, because I cannot have negative friends. Okay. And it appears that the min and the max are within a reasonable range. Okay. So I don't really have any typos. Another thing I can look at here, remember, is our group labels. Now, I can see they're clearly fine, but what you can't see is the spaces. So what if one group had like excellent space? Right? So I'm going to copy that. I can paste it in the same sheet. And remember, remove duplicates. So remove duplicates will show you what all of the values are, all the levels for this. And it looks to me like I only have 3 levels. And that's what I want. So there's no weird spellings, typos, capitalization issues here, which is good, because in JASP we can't fix it. So we need to fix it now. So I'd argue here that there are no accuracy problems with this particular data set. I can also use this to look for missing data. Remember, we talked about you can use the count thing here to calculate based on the number of rows, but it's actually really easy just to look at this one, right? But there was a way we did this before where we did count A. We highlighted everything, and I thought you could divide by just regular count, but you can't. So I'm going to divide by 11, which is the number of participants that I have, right, times 100. Okay. Now I have 100% of the data. Now I know that's really obvious, but just a reminder of how you can do that. Okay. Now for ANOVAs, you pretty much always have less columns than you could possibly, less columns than you could possibly replace. So if a person is missing one data point, you can't really do a whole lot about it, because that means they have more than 5% of their data missing. And so if the person is missing V1 and only DV, you would be making up that entire participant if you mean filled them in. And that's not really appropriate. So with missing data, it often comes down to just excluding them completely. For outliers, remember we can calculate our z-score for the outlier. Remember that's equals, and we want to type in average, highlight this column, divided by the standard deviation, STDEV, of this column. And we want to take, I'm sorry, I forgot to do one part. We click, so let me just back up. I got too excited. So we're going to do equals, open parentheses, click on this here, minus the average of the column, close parentheses, divided by STDEV, open parentheses, this column again, and then hit enter. Sorry, it's each person minus the average for that column divided by the standard deviation for that column. And the nice thing about doing that formula-wise is that I don't have to manually type in the mean and standard deviation every single time. I'm going to get my little black arrow here instead of the white arrow. I'm going to double click, and we'll see if we have anybody outside the range, acceptable range. So we're going to use a criterion of 3 and -3. So I only have 10 people. It's pretty easy to just look here. But remember, you can also highlight everything and sort low to high. Okay. I have one person whose score is further out than everybody else's, but it's not past a reasonable range. Okay, so I don't have any outliers. The last thing we're going to do is check assumptions. So I'm going to create myself a random variable. Okay. And I'm kind of doing this all in the same one, but remember, I could take this and do, if I had to delete people, I would create myself a new one, because, which I could do either way here. So this has no missing and no outliers. So actually, this is kind of our final data set. Because I don't have any typos, I don't have any missing data, and I don't have any outliers. How convenient and great. Okay. So I'm going to create myself a random variable for our assumptions checks. Or the code for that is equal rand, open and close parentheses. And we'll just double click with a black arrow on the edge of the box right here. Beep, beep. And that will give you a random variable. Now what I'm going to do with that random variable is use it to check my assumptions. So first assumption is additivity. Remember, additivity is that each variable adds something to the equation. But in this case, I only have one continuous variable. So there's no need to check for correlations because there's nothing to correlate friends with. So we're going to skip additivity. It does not apply to between subjects ANOVA. Instead, what we're going to do is test for normality, linearity, homogeneity, and homoscedasticity. So remember, we create this random variable to test our data against a random set so we can get random residuals. So we can see a picture of residuals that should be close to 0, between 2 and 2, and random. So I'm going to click Data Analysis. See how this is much easier than lots of columns. But we start hard and then we get easier. Okay, I'm going to go down to Regression. This is our fake regression analysis. Click OK. Our Y range here are the random scores. And I think we figured out it worked better if you don't include the labels. Or maybe my Excel is being dumb. Our X range here are all of our independent, our continuous variables we're checking. We want to get the standardized residuals, the residual plots. We actually don't need the line fit plots, and the normal probability plots. Hit OK. Hopefully it won't freak out. There we go. So to check for normality, use this standardized residual spot right here. Right, remember I told you last time we're not going to use any of this data up in this corner. You don't have to black it out, but I'm just showing you, like, don't look at that. I'm more interested here in the residuals. Right, so under our standardized residuals here, I want to create a histogram for my normality. And so I'm going to I'm going to highlight these, but then I'm going to remember that highlighting doesn't do me any good. So I'm going to click Data, Data Analysis, come up here to Histogram, click OK. I'm going to highlight this area here. I'm going to tell it to just stick that histogram right here. And then tell it to give us the chart. Click OK. Now it always sticks the chart somewhere up here. So here's our histogram chart. And this histogram chart is not very exciting because it put everything below 0 on the more side, but it is a good clue that this data set is negatively skewed. So I would argue that this maybe isn't normal. This is a little bit of negative skew. And once we get into JASP, we can look at the original data set a little more and see where that problem might be caused. Now, it's probably an issue of the fact that this has a bottom, right? You cannot have negative friends. And so if our data set has most people clustered towards the bottom and then 1 or 2 people towards the top, that's going to cause us some issues. Okay. And that actually would give us a positive skew. So the residuals are negatively skewed. But we can investigate this a little more by looking at a residual of the actual data. Now remember, a histogram of the actual data. Remember, the assumption isn't that the data is normally distributed, it's that the sampling distribution is normally distributed. And generally we can solve that problem by having at least 30 people. But in this case we don't. So we may have to talk about what can I do for non-normal distributed data. So that's normality. And in here, what you would do for me is paste this picture into your homework and talk about what you think has happened. So 0 is not even on this chart, or 0 I guess is right here. So is everything centered around 0? No. Okay, there's much more data to the right. So remember, you want it centered around 0 and even on each side, usually between 2 and 2. Now for linearity, I'm going to look at my normal probability plot here. Sometimes this is called a QQ plot. Remember, you can click on the little dots, right click, add trend line, and that'll give us a line here for it. Now really the line should go through 0, 0 here, but this line will help us kind of see if the data is close. And it's not very curved. Okay, this is pretty close to the line. So I would say this data is fairly linear. Right, and then the last chart here for our homogeneity. Now there's a couple of ways to test homogeneity. We're going to go over another one today. But remember, at 0 here, and then at 0, the middle here, we would like this data to be evenly spread on each side. Now it does range from 6 to 6, so that's fairly even. But 0 this way, there's only really 1 dot here, and there's a whole bunch more dots here. So the middle of the graph vertically. And the spread, there's a lot more dots at the top than the bottom. So I would say that the spread here is not great. So homogeneity, we really need to check maybe another way to look at this, because this is a little suspect. For homoscedasticity, we wanted the dots to look like a blob. You know, if you kind of ignore the fact that there's nobody here in the middle, I would say it's fairly even with one little kind of outlier. So 11 data points makes this very difficult to check assumptions, because it's just hard to know if all of these things are correct given you have such a small sample. Okay? But I would say that these are kind of okay, and I would be very careful interpreting my results given such a small sample. So knowing that, I didn't really fix anything. I didn't do anything to the data. So I'm going to take my original data set and import that into JASP. But I will upload this file online for you to look at to make sure that you're kind of following along. You will get different pictures from me, even if you're just following along on the internet and you aren't in my class, can't see this file, because of this random thing. So it does not auto-update the results over here, but obviously you'll get different numbers than I have, so you'll get slightly different residuals, but you still should come to the same basic conclusions that I have. All right, so let's close this out. Leave Excel open. Let's open JASP. All right, what we want to do is click File, Computer, and then find where you have this ANOVA file saved. And so the data set looks like what I was looking at a minute ago, so it looks pretty good. We're going to click ANOVA. ANOVA. It's very exciting. And then under fixed factors is the IV. So remember, in ANOVA, you can only have one DV. So we're going to put friends here under dependent variable, because friends actually really should be a scale variable. It just imported with the 3 circles because it doesn't have any decimals. So I'm going to move group over here to fixed factors. So we're not going to use weighted least squares in this class. Save that adventure for a different day. But you do want to make sure you have these in the right places. Over here, it auto updates with our very pretty ANOVA. We're going to click on assumption checks, and now I can get Levene's test. So Levene's test is another way to look at homogeneity, and so it tests if the variances between groups are equal. So it's an analysis of variance on variances instead of on means, and it will look at your groups and make sure that the variances are equal. There's no other way to say that, really. So I can report this statistic. So this is non-significant. Remember that Levene's is a data screening procedure, and so we would want it to be 001 before we did anything different. So this is non-significant either way you slice it. I could also look at a QQ plot, which is the same thing as that normal probability plot, except this one's a bit more standardized and includes the line. And so I can see now that maybe if I wasn't sure about linearity, looking in Excel, I can see here that it's really pretty linear. So we can check homogeneity and linearity again. Now if I wanted to check my normality again, I thought you could make the plots here, but if I wanted to check normality again, I could hit OK, go over to Descriptives, Descriptive Statistics, take my DV, friends here, and that'll give me the means anyway, but I can tell it to give me a distribution plot. So I clicked Plots, Distribution Plots. Okay. Now, the distribution of the data is really normal, okay, except for the fact that we have 11 people, but the residuals may not be totally normally distributed, which is not good, but this part is pretty good. So I would say that most of my data meets assumptions with qualifications for small sample sizes. Okay. So that's just another way to check and make sure that what you're doing looks okay. So back to our ANOVA. So we can get rid of this first ANOVA if you would like. Just we don't have it twice. So I got my descriptives, I checked this graph, I've checked homogeneity, I've checked linearity, and it matches what I had been thinking. Now here, under post hoc test, since our ANOVA, our overall ANOVA over here is significant, which is great, what I want to do is run a post hoc test. So a post hoc test allows me to figure out where the differences are. So remember, ANOVA tells you if something is significant, but not where. And we have to use our little magnifying glass to figure out where. But one thing about a post hoc test is that you have to be careful to not cheat. So sometimes it's called phishing, sometimes it's called p-hacking, just depends on the day, where you run a whole bunch of post hoc tests and just figure out which ones are significant. What we're going to do instead is sort of always talk about doing pairwise, all pairwise combinations. So we sort of know from the beginning we're going to do all of the pairwise combinations. Now you might not actually want to do that, but I'm going to teach you the way that requires the most work. So if you decide, no, I just want this one pairwise combination, you can do the easier, just run a t-test kind of thing. But we're going to plan to do all of these possible combinations. So I'm going to take group here from the left and move it over to the right. It's going to come up here at the very bottom. And that made every possible combination. So excellent to fair, excellent to poor, fair to poor. And I love this chart. I love it with a passion because what it does is it shows you all the combinations and what it's doing. And so we're going to take that information here in a minute and translate that into something that is very similar. It makes sense. Now, which one should I pick down here under correction? Well, Tukey is probably the most popular, but I know in the lecture we talked about Bonferroni, and so you can actually add both and look at the differences here. So this is really nice if you're like trying to learn how these work. What Bonferroni does is it calculates a correction on alpha. So remember, it calculates a correction based on type 1 error, and then it fixes the p-value for you. So this is not the new alpha. This is the given that we want our statistic to be less than 0.0167. That is 0.05 divided by 3. 3 because it's 1, 2, 3 tests. Given that alpha is 0.0167, what's our new found p? So remember, I've made a big distinction in one of the first lectures about alpha. It's a criterion that we're setting as our cutoff, our line in the sand, whereas p is the statistic that we found in the study. And so what happens is Bonferroni corrects on alpha and then shows you a new p-value. Tukey corrects the new critical sort of t-score that you have to find. So the new value here that would be significant. So remember in the second or third lecture we talked about you can use p-values or you can use cutoff scores. Tukey corrects that cutoff score. That has the same effect. They aren't quite the same math, but it also corrects your p-values. Now Tukey corrects less than Bonferroni, that's why our p-values are lower here. And I would say that Tukey and Bonferroni are equally popular. Pick whichever one you like, but only pick one. And I'm going to go with Tukey because it's my favorite. Now, one thing this doesn't do is effect size. So we'll come back to that in just a minute. And if you want to look at a plot, I would move it over to horizontal axis and tell it to give you error bars. But remember, we don't really like these plots too much because we can't edit them. Sorry, JASP, I love you guys, but come on, let us edit the plot. But it will help if I have something to compare to for the plot I'm going to make in Excel. So right now, what we're doing is we're getting all the information we need to then go through and make a pretty write-up of this. I already have the means from my descriptives plot up here for the overall statistic, but I kind of need the means for each group. So under additional options here, we're going to put group, move that over. And then that's going to give us the marginal mean. So that's the mean for each group. So anytime you see marginal mean, it just means mean for each group or for each level. It also gives us the lower and upper confidence interval for each one, which is really great. The only other thing we're going to have, if you can actually display descriptive statistics. So if you wanted the standard deviation instead of the means, instead of the standard errors. So what is the difference between these two boxes? The big difference is that this marginal mean one gives you standard error. The descriptives ones gives you standard deviation. So whichever one you want to report in your paper, because remember we've talked about you need to report the means and standard deviations. This one also gives you n. So that gives me sample size if I need that for any particular reason. So that's the difference here. I kind of like having both because then I don't have to take standard error and convert it myself. But you can pick which one you want to report and pick that box. Or heck, ask for all the boxes and then decide later. The very last thing I'm interested in this window is estimates of effect size. So I want to include eta squared. So I'll come up here, and that sticks eta squared here on the end of my ANOVA. So by all accounts, this would be a large effect size, which is sort of interesting because we only have 11 people. So I would say that our power is rather low, but we'll check it here in a minute. Okay. So what have we done? We have done the analysis of variance here at the beginning. We talked a little bit more about assumptions. I found that my ANOVA was significant because P is less than 0.05. I've run a post-hoc test, so we're going to cover more in just a minute what the heck that thing means. I found my descriptive statistics so I can put them into information to create a chart in Excel. Okay. And so I'm really going to use this mean and standard deviations chart, but I could do standard error, so you can do either one. And then I created a plot for comparison in Excel, and I added to my ANOVA the effect size, because one big thing about this class is that we're pushing effect sizes. So I now have almost everything I need to write this up and make a graph. The only other thing I'm missing is these effect sizes here for these post hoc tests. So I'm going to show you how I'm going to get that data, and then we'll go over to Word and we'll talk about how to interpret all of this information. Okay, so we're going to do everything in this window first. So what this does, this post hoc test box does, is it compares each group to every other group. And there's 3 groups, so there's only 3 comparisons, because fair to excellent is the same thing as excellent to fair, forwards and backwards. It gives me the mean difference, which is just a subtraction here from our marginal means box. And it gives me my t-value. So t and a corrected p-value. That does not give me an effect size for that comparison. So I know from my eta squared value up here that the overall, the independent variable accounts for 56% of the variance in the dependent variable, which is a lot. And so I know something happened. So eta here just tells me that there's a big effect. But I have the same problem with eta that I do with p. Where is that effect? And so down here, I really would like to know which of these comparisons, because only one of them is significant, is where that effect is. Are they all big? Or 2 of them small and 1 of them's big? Or does it match the significance values? Like, what's actually happening? So we want to get Cohen's d for each of those effects. Now we're going to cheat, and we're going to do this as a t-test to be able to do that. But we're going to ignore the t output that we're about to get. So we're going to use JASP to get it and then ignore some of its output, because otherwise we're kind of cheating. So we want to make sure we report this post hoc box, because it controls for the fact that we've run several tests. So click t-tests. This is a between subjects analysis, so it's independent samples t. We're going to move friends and then our DV box here, group down here, and it says the grouping variable must have 2 levels. Okay. So that's one issue here, is that it won't let me pick these levels. Okay. So there's 2 ways to fix that problem. Okay. We can either calculate these effect sizes manually, which isn't too bad, okay, or you can go through and create yourself little Excel files that only have excellent to fair, excellent to poor, and fair to poor. And it is 6 dozen one way, 6 dozen. That is a terrible analogy. It is equal amounts of work each way, or 6 one way, half dozen the other. Good grief. So while it would be great to be able to do this, I can't do this for between subjects t. When we get to repeated measures, you can. So that's the good news. But because our grouping variable has 3 and they don't quite have a little function yet where you can just say pick these 2, we can't get it to do that. So I'm going to give you another option to calculate effect sizes. So I'm going to remove that. Okay. So I have everything I need now. So I'm going to take my results. I'm just going to copy the whole thing. Okay. Let's go over here to Word. Pull out everything. Can't spell, my goodness. Open up Microsoft Word. There we go. Link document here, and let's paste that into Word. Okay, it's going to copy everything over as a picture. All right. It's going to copy all those pictures over for me very slowly. Here we go. Okay, so I have my overall descriptive statistics in a table. Don't really need that. I have my histogram, which is just unbelievably huge. Make that smaller. So you might need that for homework, but I don't need it right now either. But here's my ANOVA. Okay. So how would I report this information? Here under Levine's test, and I'm going to do this in APA style, so if you're using a different style, just remember to change it. I'm going to say that my F was 2 and 8. So we picked the degrees of freedom 1, degrees of freedom 2 here was 2.16. I'm going to go with 2 decimals. P equaled 0.18. Okay. You notice here I don't have a 0 in front of P because it doesn't get over 1. And so you don't have zeros for decimals that don't go over 1. Okay. And this is non-significant. Okay. So homogeneity was met. Okay. Now, write that in much better English. Okay. So using Levine's test, we found that homogeneity was met because it was non-significant. And then plot this F statistic in here. So here is how you would write that up. Okay. And so we used all the numbers across here. Okay. Then I would talk about my ANOVA here. And I would say my overall ANOVA was significant. It's the same write-up. F, open parentheses. Now it's 2 and 8. It goes down because nothing is consistent. Here's my F statistic right here, so 5.13. My p-value, I'm going to round up, is 0.04 here. And then I'm going to put in eta squared, and I'm going to copy eta because my Mac likes to eat the symbol. Okay. Eta squared equals 0.56. Okay. It also does not get over 1, so it shouldn't have a 0 in front of it either. Okay. So here, under my test statistic, I have F, P, and eta. So anytime you're reporting a statistic that's hypothesis testing, it should have some sort of statistic, F, T, chi-square, p-value associated with that statistic, and an effect size. Okay, so they should come in threes, right? F, P, and eta. So I would say this is significant. So my overall ANOVA is significant. Okay. Sometimes this is called the omnibus test. Or overall test. I'm going to scroll past my QQ plot here and look at this post hoc test. Okay. So one thing I always have people do when they're making these post hoc tests is to just make a comparison box. Okay. And I've done this for a couple semesters now, and it seems to help with a comprehension of what the hell is going on. So I'm going to just make a new page here so it's all in one place. And I'm going to keep my marginal means right here with me. So I'm going to insert a table. I think 4 is enough. Okay, so this is going to be group 1. So group 1 here is the excellent group. Their mean is 3. Their standard deviation, you'll see there's a reason for this in a minute, is 0.82. And in here, I'm going to use my descriptives box, so I'm getting this pretty much all from here. It's actually more, this box is more helpful than our marginal means box, is 4. Now that's also going to be group 1 for the second comparison. So just going to copy and paste that again. Group 2 here, let me save this. No idea what folder that's going to. We'll stick it in this one right now. Okay. Group 2 here is going to be our fair group. So their mean is 5.33 and 2.52 here. So 5.33. SD is 2.52. And N was 3 people. Okay, got that all from here. And that is the same group as here. So I'm comparing excellent to fair, so excellent to fair, excellent to poor. We'll get to poor here in a second. Fair to poor. So I'll copy this one, stick it here. And let's do the last group. So the poor group's mean number of friends, poor health anyway, is 1.5. Standard deviation is 1.29. So it's a little surprising the variances worked out okay, because look at the variance between this excellent group and this fair group. They're pretty different. So that might be why our residual chart looked a little poor. So 1.29. And then N is 4. Okay, all pulled from this descriptives box. Copy this, paste it here. Okay. So now I have each group. I'm going to take their comparison statistic. Okay. So in this case, they're a t, but what goes here? So we talked about how t has degrees of freedom. Okay. Now, it's an interesting question because it depends on how they ran this test, but generally it's going to be n minus 1 plus n minus 1 would be my best guess here. So I've got 4 minus 1 plus 3 minus 1. Oh my gosh, y'all are making me do math. 3 plus 2 is 5. Equals, I've got my statistic here, 1.95. And then we're going to include our p-value. And so if we think about this, this is not significant. So there's no difference between excellent and fair groups and the number of friends that they have. Now let's do excellent to poor. So we've got t. Now we've got 4 minus 1 plus 4 minus 1, which is 6. And that t-value is 1.35. Our p-value is 0.41. So this one is not significant either. So there's no difference between excellent and poor health in the number of friends. The last one here, it's going to be 3 minus 1 plus 4 minus 1, which is 5. And it would not surprise me if I mathematically could not do that, so always double check. It's 3.20. So here, comma, p equals 0.03, and this one is significant. That still has not told me what the effect size is here. So what effect size should I expect for each of these values? So that's one thing we couldn't seem to get from JASP, mainly because, or we could get it if we wanted to create 3 different data sets. So a data set with only the first 2 groups, a data set with the second 2 groups, and a data set with the third 2 groups, which is fine if you would like to do it that way. Instead, I'm going to show you this cool little program that a very smart friend of mine helped me write, which is downloadable on Blackboard or my website. So let's use this one. Now, this does require that you have Java runtime something or another installed. So if you're having issues getting this to run, please come get help or send us an email because it is not just regular Java. It's like Java fanciness. And if you're on a Windows 10 machine, most definitely come get help because Windows 10 and this program don't always get along. But the way that MOTE works, which is measure of the effect, is it's a effect size calculator. So what we can do is click measures, scroll down to independent t here, and then we can type in our statistics. So the reason I went through all this trouble to create this box is because it makes this part a lot easier. Okay, so instead of like trying to figure out, okay, this one to this one, this error, now I have it all laid out for me nice and simple. So it does take a little bit more time to make this chart, but it makes this next part much easier. So I'm typing 3 here. You do not have to double click or backspace out 0 to make this work. You can just type on top of it. So see how I have the 0 over here? I can just type straight on top of that. So 0.82. Second standard deviations, 2.52. It gives me my 2 standard errors, but I need to fix here this number. So sample size 1 is 4, and then 3. Now note that t-statistic will not match the statistic that is presented here in the comparison because they're calculated in different ways, but that's okay. You can also use it to get your degrees of freedom, so thankfully I can subtract today, which is an unusual event. And then what you want to do here is look where it says Cohen's d. So here, right here. Okay. It does give you the confidence interval of d, which we talked about being the range of expected d values. And this one crosses 0, which isn't good. Okay. So I've got negative 1.36. The Word will stop auto-capitalizing. 1.336. Okay. So I need to do that for all of them. Okay. So now I can come back up here and get this highlighted. So mean 2 is 1.5. The standard deviation for the first one is fine. Standard deviation for the second one, I think I've opened an old version of this program. It doesn't want to let me scroll down. But now I have 4 and 4. So I've got 6 degrees of freedom. Our D value is 1.39. Make sure I entered that right. 3, 1.05, 4, and 4. Great. So one thing you always want to make sure you do is enter the means, the SDs, or the SEs in the sample size. Okay? So don't forget the sample size, because one thing this does is it automatically enters 2 as the sample size, because otherwise the math in the background has a heart attack. So be sure that this gets changed to your real sample size and don't leave it as 2. Okay. So let's do the same thing here. 5.33, 1.50, 2.52, 1.29. Okay, I'm going to change my sample sizes here to 3 for the first one and 4 for the second one. Okay. And that tells me Cohen's D is 2.04. Now, what did I do a minute ago to clear all that out? I hit edit, reset data, and that will clear out your window for you. And then the version of Mote that I should have opened also has, allows you to scroll between, I don't know where it went. I had a window, here it is. This one I think is the right one. Yeah, that looks right. So let's get rid of this one so I know I have the right one open. It allows you to scroll between the windows when you click down, and it's a little bit cleaner, so that's my fault for opening the wrong one. So when I'm typing in here values, right, it lets me use the down arrow. Now, as long as I am using either standard error or standard deviation, so I make sum up here, it will auto fill in the other numbers for me. Okay. So it also has the reset function. So this is the one that you'll be able to download from Blackboard. Okay. All right, so what does that tell me now that I have these numbers? So we found a big effect as part of our ADA. Now, which effect size was large? Well, they're kind of all large, right? But effect, definitely this one. So this one is much larger than the rest, which is why it was significant, right? Because with such low sample sizes, it is definitely difficult to find a significant effect. But I think reporting all of these would be really useful, because now I can tell which effects are important. And here I can say, well, if these effects are really that large, you just really need to increase sample size because we're missing this effect because the power is so low. So speaking of power, before we go on to graphs, let's calculate power. So we really probably need a much bigger sample size to detect this effect. So let's see what kind of sample size we would need to detect that effect. And for that, I'm going to use this ANOVA box right here. Okay. So another little program. So how many programs are we up to? We've got Mote, GPower, Word, Excel, and JASP. I think we're up to 5 programs so far. Statistics is the science of opening many windows. And if you have dual screens or you can work somewhere with dual screens, your life will be a lot happier. I have mine turned off to make these videos, and it's very frustrating. So here's GPower. GPower is a free program you can download online as well, and it's fantastic. I love this program. So what we're going to do is click Test Family here and change that to F. Be aware that online there is a GPower document that outlines all of these statistical tests and all of their options in one Word document. So be sure if you're like, oh no, I need power for between subjects ANOVA, but I don't want to watch the whole video. There's a document that you can watch. You can look at all of them at once. So just a reminder. Under statistical test here, we're going to click ANOVA, Fixed Effects, Omnibus, One Way, because this is a one-way design. Okay. I'm going to leave this as a priori because we're going to see what kind of sample size we would need here. Under effect size, this is not eta, it's F. So we're going to click determine to figure out the translate from eta to F. So under effect size from means here, click effect size from variance. Click direct. And it says partial eta, but partial eta and regular eta and between subjects and ANOVAs are the same thing. So we're going to just type 0.56 from our test. Hit calculate, transfer to main. So that transferred over here to this into the F statistic, which is much more common in the medical field, but I think slowly going out of favor. Lots of people like Cohen's D. Alpha is 0.05. Power is 0.8. Remember, we set beta as 0.2, the likelihood of missing it. Number of groups is the number of levels, so we have 1, 2, 3. Okay, so hit enter. And it actually says we need 12 people. Okay. So we would actually technically only need 12 people to find a significant effect for the overall omnibus ANOVA. So this gives us the number of people needed to find a significant ANOVA. It does not tell us the number of people needed to find significance in those post-hoc tests, because clearly we'd probably need more. Now, anytime you see a sample size less than 30, if you can help it, I understand special populations of people dropping out, and sometimes you're working with a sports team and there's only 20 of them. But if you can, anytime you can make that sample size at least 30 to hit the normality assumption and the central limit theorem, you're going to be much better off. Because while this tells me mathematically I only need 12 people, I think most of us would feel like 12 people really just isn't enough to get a stable sample. I'm going to have a lot more believability in a sample that's much larger. And the confidence intervals will reflect that. They're going to be much bigger in a small sample. But this is how you calculate power, like for your homework and stuff. And if you're trying to figure out how many participants you need, this estimate of effect size might be a little too large. So let's say we just wanted to see what would happen if it were a small effect. You can hover over the window and it will show you the conventions for small, medium, and large. So let's just change that to 0.10 to get a small effect, and you'll see how big that difference is. So this time it says you need 1,000, which is a bit too many. Obviously, this is not a very feasible study. So what I always tell people to do is to use the average from their research field or previous studies, which is what we did when we calculated this one. Or if you're unsure about the average, or you think maybe the average is too high, to estimate a little lower on the effect size here. So maybe instead of 1.2, we use 0.75. So go lower on the effect size because that'll increase the number of people. It's always better to overestimate the number of people so that you don't go have an underpowered study. Okay? So that's power. So it said we only needed 12 people. I would argue you probably need at least 30 people to really hit all of your assumptions. But that's how you do it. The one last thing that we need to do is make a graph. So I'm going to go back to Excel. If you want to, you can open that graphs example document that I made in one of the last videos that will, you can just type in your numbers here. But I'm going to make this one from scratch. And hopefully this time it won't crash 1,000 times. And what I really need is my descriptives here. So first thing I'm going to do is type in my means. So I'm going to do excellent, fair, and poor. Ooh, power, got excited. And we're going to type in the means here. Do this exact same thing. Type in the standard deviations. Remember, I don't put them next to each other so I'm not tempted to make the wrong type of chart. So I've got 3, 5.33, 1.50. My standard deviations, 0.82, 2, 2.52, 1.29. I'm going to highlight these three here. Now I've got everything. I'm going to make this bigger. Go to Insert, Clustered Column Graph. This is where we're going to do all the fancy stuff to it. So I'm going to delete the chart title. I'm going to delete these little bars. And then you can kind of do the next part in any order you'd like. So I'm going to add my axis titles, horizontal, vertical. And I really didn't put this in the right order now, did I? I probably should have put poor all the way here on the left. So the nice thing is that's an easy fix. Oops, don't put there. I can just switch these two. Okay. Now if you're going to do that, be sure you also do that down here. So take excellent, kind of switch it out with poor. Now cutting and pasting sometimes will freak out a chart. I'm not using this yet, so I just did it right there. Okay. So this makes a little more sense to rearrange the data in not alphabetical order. Now that I have the entire chart's text on here, I'm going to click on the whole chart, click here, change that to Times New Roman or Arial, 12-point font. So remember, it changes everything at once. Woohoo! Under my axis title here, I'm going to change that to health condition or health group. Here we're going to put in the average number of friends. Okay, because this is the average number of friends a person in a particular health group has for the example. Clicking here on this, on the series, click chart design, add chart element, error bars, more. Click down here under custom, specify value, and this is where I'm going to highlight these three, not once, but twice. Remember, make sure they're the same. Click, 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 click OK. Okay, that's looking a lot better. What else can I do here? I'm going to fix the axis here to be the range of the data, but that's pretty close. 0 to 8 is the range of the data, so I don't really have to fix that. But I can make the line a solid line here, make it black. I'll click on this line, make it solid and black, so that I have, if I click off of the chart here, I have my solid lines around it. The only other thing here is I might change this to be grayscale. So I can click change colors here, make it all gray. And that just, remember, makes it a little easier to read with the error bars if you don't make them black. So I would say this is a really great graph for this example. And that's what I would include in my write-up. So because I have the graph, I would not really want to report those means and standard deviations again. You can, but you don't have to because you have them in the graph. But in the graph, I would say error bars represent one standard deviation, because that's what they are, instead of confidence intervals. So don't let people believe those are confidence intervals, because they are not. That's one standard deviation up and down. But in your write-up, you definitely need to include the type of statistic that you ran. So it's a between subjects one-way ANOVA, the FP eta combination, and then each of the post hoc tests. So we have these little charts here, this little chart, and I'm going to present this information. So I'm going to present excellent to fair were not significantly different, TPD. Excellent to poor were significantly different, TPD. No, they weren't, actually, sorry. And report those. Now, in lots of outputs like SPSS and R, you don't actually ever see T, so it's one thing I like about JASP, and so you'll just see P and D in my examples, but since you have T, go ahead and report it. And since this table here doesn't necessarily have it, what you could do is take this cute little table and just clean it up. So I could add, I don't know exactly what just happened there, but I was trying to add a column out here, but I don't know what it just did. Okay, so I don't know what exactly this table's doing. Let's see if we can figure it out. Oh, well, it doesn't paste this table perfectly, so you may not be able to add columns to the table directly. You can see it's got these little weird little spaces. But you could take this information to make your own table. I think with 3 statistics, you can just write it up. So what you can do is go online and look at, I have an example write-up. I don't at the moment have that separated, but it will be separated out for you guys online by the time you view this message. Okay. Where at the very end, it'll show you an example of a write-up for this. And so in this example, I know it's too tiny to read right now, but look, there's one. You can go find this on Blackboard. In this example, I actually have the means and standard deviations for each one, and you can do that too. But if you have the graph, sometimes that's not really necessary because it's already presented in the graph. But definitely presenting the statistics you have, like T, P, and D. All right, so all of that together, this big, huge, long video covered everything from data screening in Excel to the analysis in JASP with post-hoc tests. For effect size for post-hocs, we used MOTE, which you can find on my website. For power, we talked about GPower, talked about how to write this up in APA style, and how to make graphs in Excel.